The Duff Moisture Code, or DMC, is the intermediate fuel moisture in the fire weather index system, providing an indicator of persistent drying and increasing fuel availability. This introduction to the Duff Moisture Code will identify its role in the fire weather index system, highlight the fuels it is based on, outline the calculation inputs and methods, and suggest interpretations across Alaska and the Lake States. The Duff Moisture Code, or DMC, is the second fuel moisture code among three in the fire weather index system. It uses temperature, relative humidity, and 24-hour precipitation totals recorded at solar noon, and along with the drought code, influences the buildup index each day. The image here highlights the DMC as the numerical rating of moisture content for the Duff layer below the accumulated litter on the surface, or the dead moss layer below the live moss and deep feather moss fuel beds. The scales shown below the image suggest thresholds and interpretations for firefighters in Alaska and Minnesota. The DMC can theoretically reach 350, though practically it reaches only 150 to 200 in the driest of seasons. The Duff Moisture Code is a good indicator of the changing flammability for green fuel beds during the growing season. Many have used it as an indicator of lightning ignitions, using a threshold of 20. And it can be used as an indicator of fuel consumption in ground fire. This flowchart shows the calculation of DMC each day using the solar noon weather observation. Operated as a wetting and drying accounting system, the process begins with yesterday's DMC. If there is sufficient 24-hour rainfall, it is used to reduce yesterday's value, producing a rain code. Depending on the rainfall factor applied earlier, the current temperature, relative humidity, and a monthly scaling input produce a drying factor that is added to either yesterday's DMC or the rain code, resulting in today's Duff Moisture Code. The resulting DMC values have traditionally been compared week to week, month to month, and year to year. They produce excellent representations of growing season fire potential, as this graph from the upper Yukon region of Alaska shows. The orange line shows the climatological average season trend for DMC, while the green line shows the associated buildup index, or BUI. The shaded bars show the median number of weekly MODIS fire detections in the same Yukon Flats area for a 13-year period from 2001 through 2013. And the gray shading in the background shows the normal range of weekly acres burned in Alaska according to the Incident Management Situation Report summaries. The fact that these three independent data sources agree so well highlight the powerful insight that forecasted DMC out weeks and months could provide critical fire management decisions. The DMC corresponds to a 15-day or 360-hour time-lag fuel moisture. However, represented as a fuel moisture code instead of fuel moisture in percent, it is difficult to compare directly to corresponding NFDRS fuel moistures for the 100-hour and 1,000-hour fuels. This graph shows the relationship between the Duff Moisture Code and fuel moistures that it represents. The code calculation actually uses this equation each day in producing the next DMC. More importantly, it will allow us to compare DMC with the corresponding NFDRS fuel moistures. Notice how fuel moisture changes as the DMC rises at different thresholds. At 40, the DMC equivalent fuel moisture is at 330%. At a DMC of 60, that fuel moisture is fallen to 90. Once the DMC reaches 80, the fuel moisture falls as low as 63%, and at a threshold of 100, the DMC equivalent fuel moisture is down to 50%. Using that conversion, DMC equivalent fuel moistures from the 2015 season at the Hogatsa Alaska RAWs are compared to corresponding 100-hour and 1,000-hour fuel moistures. As expected, the graph shows that the DMC equivalent fuel moisture in green responds somewhat slower than the 100-hour fuel moisture in blue and faster than the 1,000-hour fuel moisture in orange. These dashed boxes show significant growth periods for fires around the Hogatsa RAWs. Notice how the DMC equivalent fuel moistures continue to dry through these periods, though the NFDRS fuel moistures have stopped falling and even begun to rise a little. Again, because DMC is configured as an open-ended moisture code, it is not easy to compare to fuel moistures directly, like these live fuel moistures produced by the NFDRS system. However, for the green landscapes of Alaska and the lake states, Duff Moisture Code does a good job of indicating the rise and fall of flammability under growing season conditions, and does so even while NFDRS live moistures are estimated at peak levels. A last point on the Fire Weather Index fuel moisture codes and measured fuel moistures. These graphs suggest the correspondence of fuel moistures in the Duff layer and the calculated DMC from the corresponding weather observations. Though there are perplexing differences that suggest that DMC produces a compromise among a variety of fuel beds, it provides important insight across those landscapes. Remember, we are assessing fire potential for ignition, spread, and difficulty of control. The fuel moisture estimates are only an intermediate step in the process. Finally, consider these points for the Duff Moisture Code, or DMC, as a persistent drying and fuelability factor. Duff Moisture Code is linked to fuel moisture in the Duff layer under a forest canopy. It depicts relative moisture content with a 15-day or 360-hour time lag. DMC is an indicator of changing live fuel resistance to fire spread and growing season potential. And Duff Moisture Code can provide an objective measure of season severity when compared to other years. This presentation is part of a series of 8 that covers the Fire Weather Index, or FWI, system. Take the time to view the others and become familiar with the entire system.